morning children, welcome back to your chemistry class. So till yesterday we finished all the four quantum numbers. Now each electron in an atom, it is fully characterized by set of those four quantum numbers. What were those four quantum numbers? The principal quantum number, azimuthal quantum number, magnetic quantum number and the spin quantum number. Now, there's one question that arises. The energy of an orbital in many electron atoms, why does it depend upon only the principal quantum number and the azimuthal quantum number? What did I say? The question is that the energy of an orbital in many electron atoms, why does it depend both on the principal quantum number and the azimuthal quantum number, correct? So the answer to this question could be like in many electron atom, an electron is always attracted by the nucleus, right? And at the same time, it is repelled by other electrons that are present in the orbital, right? So orbital always has set of two electrons, remember. So what did I say? That in many electron atom, an electron is attracted by the nucleus and at the same time it is repelled by the other electrons that are present in the orbital. That is the stability of the electron I am talking about. It is decided by the balance between the attractive and the repulsive forces. But over here, the attractive and the repulsive forces, both they depend on what? The type of shell, the shape of the orbital in which that particular electron is present. So now the type of shell, it is decided by what? Principal quantum number. Okay, and the shape of the orbital, it is decided by the azimuthal quantum number. Therefore, the energy of the electron, it always depends upon what? The principal quantum number and the azimuthal quantum number. I hope this reason is very clear to all of you. So now, today we are going to study about Pauli's exclusion principle. Okay, Pauli's exclusion principle. Now, in 1925, Pauli, he represented a principle which controls the assignment of values to the quantum numbers of an electron in an orbital. What did I say? He presented a principle that controls the assignment of values to the quantum numbers of an electron in an orbital. So, what the Pauli's principle state? It states that no two electrons, okay, in an atom can have the same set of all the four quantum numbers, right? So what did Pauli's principle state? It states that no two electrons in an atom can have the same set of all the four quantum numbers. Now all the four quantum numbers you are very much familiar with now. So over here he meant to say that an orbital, as we know, it cannot have more than two electrons. Why? Because three of the quantum numbers, that is the principal quantum number, the azimuthal quantum number and the magnetic quantum number, at the most may be same, but definitely then the fourth one will be different. Hence it says no two electrons in an atom can have the same set of all the four quantum numbers. Now suppose I give you an example, like I take an orbital, say 2pz. Okay, this 2pz, it is going to have 2 electrons present in it. Okay. So now let us see over here, according to Pauli's exclusion principle, that these 2 electrons, it cannot have the set of all the 4 quantum numbers same. So for this one over here and for this electron, I'm going to write down over here. Okay. So let us frame all the this thing. Quantum numbers, it has N, L, M and S, and for this N, L, M and S, right? So what is N over here? N, since it lies in the second orbit, so it is 2 for this also. Okay, so if it is 2, then your azimuthal quantum number, it is 1, right? Then your magnetic quantum number, maybe it is 0. But definitely see the spin. This is clockwise, this is anti-clockwise. So this is plus half and this is minus half. So what does it say? 2 of these electrons in an atom, they cannot have the same set of all the 4 quantum numbers. Here you can check that the principal quantum number, azimuthal is same, magnetic quantum number is same, but the 4th one is different. Hence, what did I say? That an orbital cannot have more than 2 electrons first and foremost, right? Why? Because 3 of its quantum numbers may be same. Principal, azimuthal, magnetic quantum numbers, they can be same at the most. But then the 4th one will definitely be a different one. I hope this is very clear. This was expressed by Pauli and therefore it is called as Pauli's exclusion principle. Let me give you some more examples, right? For example, let me take that of magnesium. I'll explain it to you with the help of an element, magnesium, whose atomic number is 12, right? So let us configure this. Now don't worry about the configuration. I will be explaining it to you in the next video maybe. So try to just understand over here the principle, Pauli's principle, right? Give more focus to the Pauli's principle. So when we configure this, we get 1s2, 2s2, 2p6, 3s2. So let us look at the orbitals. This is 1s2, this is 2s, this is 2p, and this is 3s. Now 2p, okay, let's come over here. So it will have 2 electrons, 1s2. So 2 electrons, 2s2, 2 electrons, 2p. We already know that p has 3 orbitals. So it says 2p6. So 1, 2, 3, 4, 5, 6. 2p6 and 3s2. 3p(s)2. Okay. Now let us talk about this particular orbital which has 2 electrons. Okay. No 2 electrons in an atom can have the same set of all 4 quantum numbers. Now let us understand the 4 set of quantum numbers of these 2 electrons. Fine. So let's talk about the principal quantum number. This is placed in which? 3rd orbit. So both are the same, right? Now let's talk about L, the azimuthal quantum number. That is for both are 0. Go back to the formula that I had taught you yesterday. Then you will understand this. Then what about the magnetic quantum number? For both will be 0. Right? Now let us look at the spin. Now for this it is upward, so it is plus half. For this it is downward, so it is minus half. Now look over here. The principal, azimuthal and magnetic. Principal, azimuthal, magnetic. These are same. But what is different? The spin quantum number is different. So at least one of the quantum numbers should be different. The address of both the electrons cannot be same. Clear? Okay, this was when I had compared these 2 electrons in the orbital. Now I am going to change the orbital and let us then find out the difference between the two electrons. So let us take this one from here, which I have already written, and let me from here take this one. Okay, this electron. So this is already ready with you. I'm talking about this set. Okay, now let's talk about this. The principal quantum number, it is 2, right? Then what will be L? If the principal quantum number is 2, then L is always 1. Then what is the magnetic quantum number? It is 0. What about this spin? Now look at this spin. It is going upward, so it is plus half. Now compare this and find out the quantum numbers, whether all the 4 quantum numbers are the same or different. So over here, the principal quantum number is different. Then your azimuthal quantum number is different. What is same? The magnetic quantum number and the spin quantum number. Only these two are same. So what did we understand? Hence, no two electrons in an atom can have the same set of all the 4 quantum numbers. I hope this is very clear to all of you. Over here, you must be wondering, why did I take m is equal to 0, the magnetic quantum number, as 0. So do try to understand that the 3 orbitals of p are px, py and pz. So I have taken from pz, and remember, for pz m is always equal to 0, right? For px and py, m could be plus or minus 1. It is not fixed. It can be plus 1, it can be minus 1 as well. And therefore, since I took pz over here, therefore I took mo as 0. So I hope this Pauli's exclusion principle is very clear to you. You can take the comparison of any other electron also. Like for example, let me take this. Let us talk about this s orbital. So we have 2 electrons. Let us talk about these 2 electrons. Okay. So I am first writing for this one. Over here, n is equal to 1. Then L will be equal to what? 0. M will also be equal to 0, but the spin will be equal to what? It's going upward, so it is plus half. Let's talk about the second electron. Here n is equal to 1, right? L is also equal to 0, M is 0, but what about S? It's moving downward, so it is minus half. So you can see over here, the first 3 quantum numbers are same, but the fourth one is different. In this way, we understand what is Pauli's exclusion principle. Clear? So, since the set of the 4 quantum numbers of an electron in an atom, it is unique. Therefore, a particular shell in an atom can accommodate as many electrons as are possible sets of 4 quantum numbers for it. So on the basis of this conclusion, maximum number of electrons that can be accommodated in an orbital, a subshell or a shell can also be determined. So let us further go ahead to understand and how to calculate the electron capacity of an energy shell. So let us talk about firstly the K shell. Do you know which is the K shell? That is the first shell. So what do we write over here? N is equal to 1 shell. Okay. So if N is equal to 1, then your azimuthal quantum number will be equal to how much? 0. Then what will be your magnetic quantum number be equal to? 0. But over here spin will be what? One will be plus, another will be minus. There are 2 different sets, right? So keeping in view this Pauli's exclusion principle, we make maximum number of 2 sets only over here in the first shell, right? So this you can understand like this. This is one electron, this is the other one. So for each of them, as I told you, you can divide it into 2. For divide it like this. This for this one and one is for this one. So over here n is equal to 1, l is equal to 0, m is equal to 0, but s is equal to, this is going down, minus half. For this one, n is equal to 1, l is equal to 0, m is equal to 0, and s is equal to, since it's going upward clockwise, it is plus half. Clear? So two sets are formed, right? So this was your first shell. Therefore, this K shell can accommodate how many? Maximum of 2 electrons, which are also of the opposite spins. Now, since this K shell contains only one subshell, right? That is the S subshell, which in turn contains only one orbital, which is what? Which one it is called as? 1s. Always remember, it is written as 1s, and this can be concluded that maximum of 2 electrons can be accommodated in this orbital, and they all possess what? Opposite spins. Is this K shell very clear? Now let's talk about the L shell, KL. Okay. So when I'm talking about L shell, which shell am I talking about? Shell number 2. So when n is 2, when n is equal to 2, then your L can be 0, it can be 1. Okay. Then what about your magnetic quantum number? It can be, if n is 2, L is 0, then m will be 0. But if n is 2, L is 1, then m can be plus 1, 0 or minus 1. Okay. So these are all the possibilities. What? When n is equal to 2, L is 1, then m is plus 1. Then what will be your S? The spin quantum number for each magnetic quantum number will be 2, plus half and minus half. Is this point clear? So over here, S for this will be plus half and another will be minus half. And for these also, for each value of M, it will be plus half and minus half. Thus, in this L shell, it contains how many subshells? The second shell contains how many subshells? 2s also we write and 2p also we write. When we talk about 2p subshell, that means what are we talking about? We are talking about 3 orbitals. What are they? px, py and pz. So it is 2px, 2py and 2pz. Okay, I'll write it down like this. So in total, how many orbitals are there? 1, 2, 3, 4, because 2p is divided into 3 orbitals. So 3 from here and 1 of 2s. So total of how many orbitals? 4 orbitals are present over here. Right? And since 4 orbitals are present here, so how many electrons can be accommodated? 2 in S. 2 can be accommodated in S, and in each of this 2, 2, 2. So 2 plus 6. 2 plus 6. That means 8 electrons maximum can be accommodated where? In the L shell. Is this point clear? Now, let us see all the possible sets of the 4 quantum numbers that we can see in the L shell, right? That I was explaining you over here. So let us observe like this. If n is equal to 2, then L can be, as I told you, it can be 0. Then if L is 0, then m is equal to 0. Then spin is equal to half, plus half and minus half. Okay, this is two possible sets of the which orbital? This will be for S block. Okay, S subshell. So again I am writing 2, L is 0, M is 0. Okay, S is equal to minus half. This is for 2S. Is this clear? This is for one. This is for the second one. Now let's talk about 2px, 2py and 2pz. So when n is equal to 2, then L will be equal to 1. Then m is equal to plus 1. Then s is equal to plus half. Okay. For the second one, n is equal to 2, l is equal to 1, m is equal to plus 1 and s is equal to minus half. Okay. Now let's go to the 2p y orbital. N is equal to 2, l is equal to 1, m will be minus 1, s is plus half. For n is equal to 2, l is equal to 1, m is equal to minus 1, s is equal to plus half. Okay, which one am I talking about? This one was for px. This one was for px. Now I'm writing for py. Okay, two sides are done. Now for pz, n is equal to 2. Okay, then l is equal to 1. And do you remember just now I told you when we take pz, then m is always 0. M is 0. S will be, this I made a mistake, minus over here. So this becomes plus. N is equal to 2, L is equal to 1, M is equal to 0 and S is equal to minus half. This is for PZ and this is in total for which subshell? 2p subshell. So 2s, 2 electrons and 2p, 2, 2, 4, 5, 6. So what have I written here? 2 plus 6, 8 electrons in total can be accommodated in the L shell. I hope this is very clear to you. Now let's talk about M shell. Let's talk for M shell. So if I'm talking about M shell, then N will be equal to what? 3, right? So over here, when N is equal to 3, then your L could be equal to 0, it could be 1, it could be 2. Okay? If L is 0, then M is also equal to 0. But if L is 1, then it can be plus 1, 0, minus 1. But if L is equal to 2, then plus 2, plus 1, 0, minus 1, minus 2. And for each, S will be equal to plus half and minus half. Okay. Now, let us talk about M shell, which contains how many subshells? M shell contains how many subshells? So, we find the subshells found in M shell are 3s, 3p and 3d. Okay. So 3s, that means 1 orbital, 3p means 3 orbital and 3d means 5 orbital. So 5, 6, 7, 8 and 1, 9. Total of how many? This has orbitals I'm writing over here. So you will understand 1 orbital here, here 3 and here 5. So 1 plus 3 plus 5. How many orbitals are there present in your M shell? 9 orbitals are present in the M shell. Let's see what are those 9. This is only 3x. Then this will be 3px, 3py, 3pz. And what about the D1? D1 will be 3dxy, 3dxz, then 3dyz, then 3dx square minus y square. Do you remember all these? I had taught you yesterday. Then 3dz square. So how many orbitals of 3d? 1, 2, 3, 4, 5. From there, 3 of p subshell and 1 of the s subshell. So if we are going to write down all, how many electrons in total are we going to find over here? Let's see. 2 present here. Okay. Number of electrons. 2 are present here. How many here? 3 2s are 6 are present here. And here how many? There are 1, 2, 3, 4, 5. 5 2s are 10 are present here. So in total, how many electrons are you going to find in this M shell? Total of 18 electrons we are going to find over here. Okay, I hope this is very clear. Go ahead, showing you the distribution. Okay, so let's talk about n when it is equal to 3. Then I'm talking about S shell. Okay, then L is equal to what? 0. Then M is equal to what? 0. Then S is equal to half. Okay, then n is equal to 3, L is equal to 0, M is equal to 0, S is equal to half. This is for the 3s subshell. Clear? Two possible sets are found over here. Now next, when n is equal to 3, L is equal to, what did I say? If it is plus 1, so 1, then M is equal to plus 1, S will be equal to plus half. Then the second one, n is equal to 3, L is equal to 1, M is equal to plus 1, S equal to minus half. This I am talking about which one? 3px, right? Now n is equal to 3, L is equal to 1, M is equal to minus 1, S is equal to plus half. N is equal to 3, L is equal to 1, M is equal to minus 1, S is equal to minus half. This could be for 3py. Now n is equal to 3, L is equal to 1, M is equal to 0, S is equal to plus half. N is equal to 3, L is equal to 1, M is equal to 0. S is equal to minus half. This is for 3pz. So in total, this is for the 3p subshell. This is the 3p subshell. How many electrons are we getting over here? 6, right? Now let's go to, this one was when L was equal to 1. Now same set we are going to write for n is equal to 2. So let's see that also. N is equal to 3, then L is equal to 2, then M will be equal to what? M will be plus 2, then S will be plus half. N is equal to 3, L is equal to 2, M is equal to plus 2, then S is equal to minus half. This way you just continue doing it. So in total this is I am writing for 3D. Okay, 3D shell, what? 1 for 3D XY, 2 set for 3D XZ, 2 set for 3D YZ, 2 set for this, 2 set for this. Each orbital will have 2 electrons, so total of 10 electrons will be found over here. So in total how many? 18 electrons are found in the M shell. I hope you have understood how to fill the electrons in the different orbitals. Okay, so now for you, calculate the electron capacity of the N shell. I did K, L, M. Now you have to do it for N shell and see if you are able to do it like this. Okay, now the next two principles that we need to understand is the Hund's rule and Aufbau's principle. Okay, with these two principles I will be talking to you in the next video, that is tomorrow, and both these principles are very important. So when I'm going to send the video tomorrow, please understand all these principles, the Pauli's exclusion principle, Hund rule or Aufbau rule, or the different ways of filling up the electrons in the orbitals. All this is very important. So I stop over here and I'll be back tomorrow with the other two rules. Thank you.